So in this session, we are going to talk about how PCs that are connected in a shared medium, how they are actually sending and receiving the frames. So in the data link layer, when a packet is being sent by a PC to another PC, it's called as a frame. So in this video, we are going to dive deeper and understand how this actually works. So just a recap, a LAN, basically it is, as we have gone through it in detail in our previous session, what we call as a LAN is a shared medium, and there are a lot of PCs connected to that shared medium. And the shared medium, it could be represented as a line here, but it could be a devices like a switch. It could be multiple switch connected, and we will go deeper into operations of the switch, how switch can be configured, how switch actually works in upcoming sessions. So but for today's session, just understand this, it is a shared medium. That means there needs to be some rules in place on how to use this shared medium, and we're going to cover that particular aspect of it in this session. So when you are actually having two PCs, it's pretty simple, right? One PC1 sends it, and PC2 receives it, and it actually processes it. But what do you need to understand is, and it is this is going to be true for any devices that you are going to learn in the upcoming sessions, routers, switches, or anything, right? If you go and search for so when a PC is connected, or when any device is actually connecting to this LAN, or there is an interface card that is actually with the PC. If you have seen your PC, you will be able to see that there is a thing called network interface card, which connects to the shared medium. Now there is a specification for each of these interface cards. So one thing that actually defines the network interface card is the buffer size of it. What that means is how many number of frames I can actually buffer on my NIC card before I send across into the shared medium. And similarly, at the receiving side, what happens is it is actually having a receiver buffer, and it puts these frames when there are multiple frames, multiple communications happening, and if the CPU needs to be used in an optimized way. At the receiver side, all these frames that are actually receiving here, it needs to be buffered, and there is a buffer called the input buffer. So there is a sending buffer and there is a receiving buffer, and there is sending buffer and receiving buffer for both the sending PC as well as the receiving PC. One of the for the PCs, it still doesn't really matter, but for the devices like routers and switches, one of the thing then when you design a firewall or design a switch or a router as a hardware engineer, one of the thing they will be considering as an architect is how many number of frames or how many number of packets these NIC cards will be able to put it in the buffer, right? And once you have it in the buffer, then how it actually processes out, how it actually processes those packet is the internal architecture of the system. But at least these buffers that are actually provided by the NIC cards, that is standard across the industry, because these network interface cards are provided by companies like Intel, Broadcom, etc., right? So what vendors do is, vendors like Cisco, Juniper, Arista, what they do is when they design their firewall or when they design their switches, they consider the vendors like Broadcom and Intel and that kind of companies, and then see which will be the company that will be able to provide the maximum or the optimal amount of input and output buffer. And that is one of the criteria for the vendors who design the system to select which interface card to be used. So net there is a buffer for a sending PC and there is a buffer for receiving PC, and then once it receives, it actually sends the frames to the upper layer. Now how are the frames sent? So let's say this PC here, he want to send the packet to one of the PCs down here. Okay, so what it does is it doesn't immediately send the packet. What it checks is, as I mentioned, this is going to be a shared medium. That means this medium can be used by other PCs also at the same time. So what it identifies, this PC does is it actually first do a sensing. and this process is called actually sensing, wherein it actually checks if there is any voltage, because at the physical layer it's always ones and zeros. So it actually checks whether this medium is free. So first it does is it actually senses whether there is a communication already happening in place or not. Once that is actually sensed, it actually, and if it sees that there is no communication, or the medium is, even though it is a shared medium, it is not used by any of the other PCs, it starts sending the packet. So now let's say you want to send the packet from here to here, it actually sends the packet. So what it actually does is it senses the medium first to make sure that the medium is available for him to send the packet. Now what happens is, let's say when this PC was actually sensing, at the same time this PC was also sensing whether this medium is being used or not. And when those both sense at the same time, both identifies that there was no the medium was actually available to both of them, and then both of them starts sending the packet at the same time. At that point in time, again remember, these all are ones and zeros, these all are voltages. What happens at that point in time is there happens something called collision, because the message indicated in red sent by this PC and message indicated by blue by this PC both gets collided, and then it actually corrupts the frame that has been sent by each of them. So there should be a mechanism that is being used that has been implemented by each of these PCs to sense it properly. And when this kind of thing happen, there should be a mechanism for other PCs to know about it. So now what happens is, when both of these PCs send the senses and send the message at the same time, this particular scenario where the frames get corrupted of both the PCs is called as collision. So the algorithm that we are going to learn is CSMACD, and in that C stands for collision sensing, right? So this is collision. Whenever two PCs at the same time senses that the medium is available to them and they try to send the packet, there happens something called collision. Now what happens when the collision actually is detected? The moment the collision is actually detected, both the PCs start to send the packet for a fixed amount of time, and that is something called as jamming. What is being done, why is this being done, is to let all other PCs in the same shared medium know that there has been a collision that has been occurred. For that particular reason, it actually sends something called jamming signal. So now all the PCs actually knows that there is a collision that has been happened. Now the need of that is, it needs to, all the PCs needs to wait for a fixed amount of time, random fixed amount of time, so that before it actually tries to send anything. That is why this jamming signal is being sent. Okay, and now what happens is, again, it actually waits. Once the jamming signal is done, it doesn't immediately send. It actually waits for some amount of time, which I already mentioned, and that particular thing is called backing off. It should not send immediately. It has to wait for a random amount of time, and that particular thing is called as backing off. Now what happens is, the PC attempts to send again after it actually waits for that particular time, which is called as backing off. It starts sending the packet again, and this time again it does the same thing. It actually senses it, and if it finds that the medium is available, then it starts sending it, and hopefully this time it actually doesn't hit any collision, right? For example, now since there are a lot of PCs in the network, let's say again collision happened. It actually attempts for around 16 times to send the packet. If in 16 times it's still not able to, then it actually discards the packet. So every PC, in the PC it will not be shown, but at the switch when you see, there will be a command for you to identify and see whether there is a packet that has been dropped or not, and there is a counter for that which actually says that discarded the packet after retransmission attempt. So we'll get to that later, but do understand that there is a upper limit for the attempt. It is not like it continuously does that. At some point of time, it is going to decide that no, I'm going to discard this particular packet. So now what happens to the receiving end? So the receiving end has to make sure that when the packet has been received, it has been received in such a way that the packet is not corrupted. So there are a set of procedure for that as well. So literally, before we get into the details of how a received frame is being processed, it's very, very important for us to identify the packet structure and how the Ethernet frame looks like. So let's get into how the Ethernet frame looks like. So this is a Ethernet frame format, and we'll get into each of this thing here right now. An Ethernet frame can be 64 to 1518 bytes. We will come again and again to this number 1500. We will call it as sometimes MTU. You will see that being used in upper layer as well. But right now, do remember the byte size of an Ethernet frame could be 64 to 1518 bytes. Okay. Now, what all things are there in the header? First thing is something called preamble, and the second thing is stat of frame delimiter. These two fields, the first preamble is 7 bytes in length, and the second one, which is stat of frame, is 1 byte in length. This combinedly tells a receiving PC that a frame has been arrived, and this is the starting of the frame. The next thing is, of course, the destination address. It needs, once the frame is been received by a host or a device in the Ethernet medium, it needs to identify whether this frame was intended or destined to him. So it actually just checks the destination address of that. So that is why we need to have a field called destination address, which you actually see here. The next one is the source address. So it actually tells you who is the source, who has sent this particular frame to the receiving PC. And once it identifies that, there is a process called ARP table. We will get into that later, but do remember the frame is having something called the source address. And remember, the source address and destination address is 6 byte. That is 6 into 8, 48 bits. Now remember, this 48 bits is nothing but the MAC address of the PCs. The sending PC's MAC address and the receiving PC's MAC address. Make sense? And we'll in one of our lab, we are going to do the same exercise, and one of the exercise that you guys has to do is identify what is the source address and what is the destination address of the sending versus the receiving PC. The next is the length byte, which actually tells you what is the length of the total length of the frame as such. Now you have the data, and why you need to have a length byte? Definitely because it can actually range from 46 to 1500. That is why you need to have a length field there. And here, whatever is called as data, this is the actual information that has been sent from the PC1 to the PC2, sending PC to the receiving PC, right? This is the actual data, and that data can vary from 46 to 1500 bytes. And the last one, very important one, 4 bytes CRC. Basically, this CRC, or the frame check sequence, FCS, is something that actually helps the receiving PC to understand that the frame that has been sent is not corrupted. What it actually does is it actually calculates the FCS value, the frame check sequence value of the entire data that has been sent to it, and then it actually checks the data with whatever has been sent in the FCS. So both it calculates the FCS by itself, and then it checks that value is matching the value which has been sent by the frame. So if the value matches, then yes, the frame is not been corrupted. But if the value doesn't match, that means on the way there was a collision that has been happened, and the and the frame has been corrupted, right? So now, since now you have an understanding of how the Ethernet frame works, let's see what happens at the receiving end. As I mentioned, it actually goes and check the preamble and the start of frame. Now it understands, okay, the frame has been received, and here is where it actually starts. And then it waits till the end of the frame, because it needs to get the entire frame before it actually processes it. And how does it identify the end of frame? There are two ways. One is that it doesn't sense any signal, and then it assumes that there is a frame that has been completely acquired. And then only it actually starts the processing. So it actually waits for the signal to be or basically the the medium to be nil, or medium to be not sensing anything, right? So it actually waits for the end of the frame. And then it actually checks the FCS. Why it actually checks the FCS is because if the frame has been corrupted, then there is no point in checking the destination address and the data that has been sent, right? The moment it understands that the frame has been corrupted by checking the FCS, it can immediately discard it. So, and it actually immediately discards in that case, and then actually increase the counter for the FCS error, and then says, I'm not going to process this packet. But let's assume that FCS was fine, the frame check sequence was fine, the CRC was fine, and then what it next does is it actually checks the destination address. And destination address can be of two, right? One could be the physical address of the receiving station, that's my receiving station, or it can also be a multicast address this station should listen to. And one example is if this PC, or let's say this is a router, and it is participating in a protocol called OSPF. OSPF actually sends all the things in multicast. So then if the router's interface is configured for the OSPF, that means it also needs to listen for the multicast address. And once we talk about multicast, we will go ahead and then talk about how the destination MAC address gets converted into a multicast MAC. So right now, understand that it actually checks the destination address, and it sees whether it's it sees whether the physical address is the receiving stations, or if it is a multicast address that this PC was configured or registered to listen to. So that's how the PC sends and receives the frames in a shared medium, and this thing is actually called as CSMACD. That is the algorithm which actually all the PCs are implemented for sending and receiving the frames in the Ethernet. Thank you.